the most counterintuitive aspect of this for me is how do you make something which is soft to deform yet stiff to support loads, to be able to incorporate different functions. And it turns out that for a lot of, at least in my lab, a lot of things that we want to do, we often are stuck in this position, right? Where it has to be soft, but it has to be stiff. And for us, that's an exciting place, because then you can begin to think about incorporating, new materials, new geometries. Kind of, even as you mentioned, Marwa, early on, was, how do you power it without giving it power, right? How do we maybe harvest energy, or how do we get energy from the environment that we can utilize for what we need?
In this podcast, I'm sharing my passion and curiosity for soft robotics, where we share inspiring stories about the work we do and how we can push the limit. I am Mara Dwini, and this is Soft Robotics Podcast. Support for this show comes from Science Robotics Journal. I really find Science Robotics to be a great resource for reliable and tangible research, where we can really push the limit of the science we do in robotics. Great way to stay up to date with the published article is checking out the released monthly issue. All the links will be included in each episode description. We will also happen to have a regular conversation on the most published science robotic articles, where also you can contribute with your question and thoughts about the research. Thanks Science Robotics for sponsoring Soft Robotics Podcast.
So first of all, congratulations for the paper, and I think it's very interesting if you can maybe tell briefly the paper idea about shape morphing and why it's very interesting. Maybe we will listen to what shape morphing actions of robotics.
Yeah, sure thing. So when we started the project a few years ago, we wanted to work on this, I think, pretty large challenge in soft robotics, where you want to have a system which is soft and highly deformable, but still be able to support loads. And this kind of contradiction between soft enough to deform yet stiff enough to support loads that may be required for different functions, whether that's grasping something, or perhaps allowing for locomotion, or even maintaining a shape to protect something else. So when we set out to kind of explore this and try to, I guess, solve this problem, we wanted to make something that was soft enough to deform, yet rigid enough to maintain shape, and ideally be able to go between different shapes, and while you're in a specific shape, hold that shape without consuming any power. So that was kind of our approach to this shape morphing concept, was to have something which not only changes shape, but can maintain those shapes and maintain that shape without consuming power, and to go between different shapes. So to kind of, I guess, tackle that, essentially we wanted three things: a material which could achieve complex shapes, hold that shape, and then be able to go to a different configuration, and to do this over many cycles. So, there's been a variety of ways people have approached this problem of shape morphing in the past. And the way that we ended up kind of coming at this problem was we took three different components that we brought together. We combined concepts in kirigami engineering. We also took some inspiration from phase change materials, which allowed us to create what we called these metal endoskeletons. And then we also incorporated a embedding heating element that allowed us to activate some of the shape change characteristics. So those were the three essential ingredients: these kind of kirigami structures, a metal endoskeleton, and then this embedded heater. And those three components came together in what we called a kirigami composite sheet, where it was essentially a sheet of elastomer, so a soft deformable material. It had this metal endoskeleton, which was this kind of architectured piece of Fields metal, which is a low melting point alloy. And we also used liquid metal heaters that we kind of incorporated as an additional layer near these metal endoskeletons.
Great. Maybe I want to ask you here about. I think it's very interesting the three structures you mentioned in the paper. But I want to ask you when it comes to shape morphing, do you think the material architecture, how much of one of them is more significant to achieve shape morphing, the material part or architecture?
Yeah, so I think that's an excellent question. It's something we really thought a lot about. Um, and I guess kind of the conclusion that we came to in our paper, and I think what really allowed the capabilities that we showed, again, this shape morphing, locking, reversibility, and the ability to achieve complex shapes. I would actually say that it was really the combination of the structure as well as the materials that we used. So let me elaborate on that a little bit. So kirigami, origami, these kinds of structural approaches for shape change have really opened up a lot of possibilities, I think, for the field to go from something flat to something, highly curved or have, curves where you would want them. Um, and it turns out that some of those architectures are stable. So in other words, if you take a flat sheet, you can change the shape of that sheet, and in some instances, depending on the folds or the cuts, there are certain geometries that will be stable. So you can effectively change the shape, let it go, and it will stay there. So that's effective, and it is something that could achieve this highly deformable yet also load-bearing configurations. Um, but it turns out that in a lot of those instances, one of the challenges is that the shapes that you can achieve are often uh, designed in prefabrication. In other words, you often have a sheet of material that is designed to go to a certain set of configurations, and that's one of the beautiful things about the kirigami origami approach is that you can achieve these really interesting shapes. However, one of the challenges within those still is that they're often composed of something which is thin, something which is soft, and in many instances, those structures are not able to support loads in multiple directions. And additionally, again, they are often prescribed for certain configurations. So I think one of the things we really tried to do in this work was leverage some of these capabilities in terms of highly deformable structures, but introduce, I think, new material concepts into those structures, which then allow us to achieve really any kind of shape configuration that we want that can be load bearing in multiple directions. Um, and that material also allows us to be able to go reversibly between different configurations. So the material aspect that we incorporate here is this metal endoskeleton. And this is again, it's a low melting point alloy called Fields metal, which melts around 60 degrees Celsius. And people have used this for phase change, stiffness tuning in the past. So in other words, at room temperature, it's solid. Once you go above 60 degrees, it's a liquid. So that allows you a large range of stiffnesses. So one of the things that we did here was we took some of the characteristics of that metal, and we then essentially structured that metal into this kind of highly architectured kirigami-like geometry. And we kind of embedded that within this elastomer that has the origami or kirigami-like structures. And what that allows us to do then, so for example, with our sheet, if you take it and you can actually stretch it, and when you let go, it will maintain the shape that you let it go in. And then if you take it again, you can stretch it further or in a different direction. It will then go and stay into that new configuration. And the reason that's important is, again, now we don't have to prescribe the specific shape that we're targeting beforehand. We can actually, in this case, we made essentially a homogeneous pattern that was the same across the entire sheet. And we use that metal to actually lock in those different configurations. And I think one of the interesting things that we did in the paper was we actually leveraged a common failure mechanism in materials, which is called plasticity. or plastic deformation. So, a lot of times when you're taking engineering courses, you're learning about, preventing plastic deformation or preventing yield, because that is often failure. However, for soft material shape morphing, it turns out that when we take that metal and we deform it, what actually happens is that near the ends of the kirigami cuts, the metal endoskeleton plastically deforms. And what that allows us to do then is when we stretch something, we induce plasticity locally, and that then allows that shape to hold in position, because that deformation, plastic deformation, is permanent. So that was the advantage of using the metal. But as I kind of led with, we also wanted to maintain reversibility. And the important part about using the low melting point alloy is that we can actually heat it up to, reasonable temperatures, 60 degrees Celsius, and it will then go into a liquid state. And then at that point, the elastomeric membrane that it's in is able to effectively pull it back to its initial configuration. So this is where we kind of introduced this mechanism that we called, reversible plasticity. So leveraging what is normally a permanent deformation, but making it reversible through material selection. So again, I think, a lot of what we tried to accomplish here was leveraging the advances we've seen in origami and kirigami for structural reconfiguration, but also, introduce maybe some material concepts that will allow us to kind of push that further.
This is really excellent idea. Maybe I want to ask you when it comes to the heating, embedding heating and the structure, and to change its shape here, reconfiguration. Do you think there's alternative to heating here? If you think maybe beyond heating in the process before, finishing this idea, if there's any approach do you think, or maybe challenging to achieve what heating is doing here?
Yeah, sure. So we did, in this case, in this paper, we do focus on, so the plasticity allows us to go to different shapes, and that's great. However, if we do want to effectively, without touching it, allow it to go back to where it started, that is the point that we introduce the heating component. So again, we can take this, we can change the shape of it, put it in different configurations, and it will stay there. You can take that and then you can put it into a different configuration again, and it will stay there again. However, the heating is really useful because it allows us to effectively, send this somewhere and then turn on the heaters and then have it change back on its own accord. We don't have to touch it. So, I mean, I'll say that, some of the challenges with heating, there are a few of them, and certainly they're the ones that I think a lot of people in soft robotics are dealing with. Heating is often power hungry. It does require a fair amount of energy to heat up materials to allow them to go through a phase change. So, for us, we only have to turn on the power when we want it to come back. So we don't have to do it in between. So we can save some power that way. And additionally, when we're deforming it initially, we don't have to heat it up or turn it on. We effectively can do it in kind of the passive state. And then I will say one of the practical challenges with utilizing phase change, or in fact creating heaters, is actually the creation of the heaters is pretty non-trivial. Making a heater that can go to really large deformations and still be able to heat up that material was certainly one of the challenges in this project, where we spent a fair amount of time engineering the effectively the structure of those heaters, the way that we fabricate those heaters, and we were able to get those to work in these highly deformed configurations. But that was certainly a challenge in this project, and I think is something that we can improve in the future. And there is a lot of work right now of people developing better deformable heaters, let's say. And then I guess to think about what's next, maybe beyond heating, like are there other mechanisms that we could use? So I mean, broadly, there's a variety of stimuli people have used. I think that we've seen a lot of shape change morphing recently with magnetic materials. which I think is a really interesting area. There's been a lot of inspiring work there. We've also seen people use things like pneumatics to morph materials, which has been a very common approach. And I think, the mechanism that we're using here with these metal endoskeletons, it seems like heating is an important aspect of that. But I'll also say that I think moving forward, we're also looking at different actuation schemes that we can incorporate with these metal endoskeletons that would allow us to achieve some of the same kind of functionalities, maybe reduce some of the power that may be needed for heaters, and then try to effectively make it so that we have very reliable, spatially controlled ways of changing shape across a sheet.
Yeah. Maybe I want to ask you again about the structure, maybe in the heater and also the pattern you see in the paper. Do you think that how we can design a structure to minimize, for example, the energy consumption here or increase sensitivity, or how we can achieve that in structures?
Yeah, I think that's great. So, very good question because, in this case, we did that to an extent. So, in our work, we in the paper, I guess there's a few components to it. We kind of developed and studied these kirigami composites. We explored and quantified how well they maintain shape upon deformation. And then towards the end of the paper, we take these composite sheets and then utilize them for a few different robotic demonstrations. So the first demonstration that we show in the paper is a multifunctional drone. And in that case, we have a sheet of the kirigami composite, and we also incorporate the different components that you need to have a drone, as well as something that can drive on the ground. And I think I'll get into more details about that later, but to get back to the heating point, which was that effectively what we did in that demo was we had the sheet initially in a U-shaped structure, which allowed for the driving mode. And then we would activate the heaters in this case to take that U-shaped structure, morph it into a flat shape. And then that flat shape was what we used for the quadrotor drone. And in that instance, we actually only put heaters around certain areas of the endoskeleton that we needed to transform from the U-shape to the flat shape. So I guess that's a pretty long-winded answer, but we can specifically locate heaters to enable the morphing that we need at that moment. And I think that's a really promising solution generally for heating in terms of phase change is being able to localize, not have to heat the entire structure. And the other advantage that you'll get too is, in this case, most of the things that we worked on were sort of, let's say, hand scale. You could hold the composites in your hand. The robots were about hand size. But as you decrease size, it turns out that the time it takes to heat, the time it takes to cool, the amount of power you need to do phase change, they all go down. So as you get to smaller and smaller scales, the performance of heaters, of phase change mechanisms gets better and better. And we've seen this in some really great work by a couple different groups now, where when you get down to these, tens of micron scales, or maybe even a couple hundred microns, heating and cooling can be much more rapid, which then can increase your frequency of operation. So I think, spatially locating heat, potentially downscaling the systems in specific areas, I think those are promising avenues we can take to improve performance of these, thermally activated processes.
Great. Maybe I want to ask you again in this point, when you localize the heating in a certain point to achieve this transformation, do you think you can achieve that slowly based on the intelligence and structure, just slowly in the material part without any stimulus? Do you think it's something could be done or challenging?
Yeah, I think that's really interesting. So could we, instead of having to, I guess, power it externally, almost power it kind of internally to the material? Yeah, I think that's really interesting. Right now, for at least what we did, we definitely just powered it externally. But I do think as we go forward, embedding those functions more deeply into the materials, I think is really an interesting aspect. If we could offload a lot of the components we need for heating, the electronics to control the heating, and essentially embed that into the material itself, I think that's really a promising avenue. I don't know right now how exactly we would implement that at the moment. I don't have an answer specifically to your question, but I think that's a really enticing possibility, or maybe even using some of the energy from the local environment that you could focus in uh, to activate these kinds of processes. That could also be interesting. I guess the other thing people have been looking at would be chemical reactions. So we're sort of using resistive heating right now. So we're effectively passing a current through a wire. It heats up, and we utilize that heat to induce the phase change. But if you could have certain elements of the material be chemically reactive to different chemicals, you could certainly imagine having these exothermic reactions that produce a lot of heat that maybe would allow these kind of phase changes to occur. And I think that would be a really nice way to do this. There's a lot of energy in chemical bonds. And if you can leverage that energy, you could probably do a lot of very nice things in terms of supplying heat.
Maybe I want to ask you again about shape morphing. There's other interesting functionality when you see the transition from certain shape to another. When you think about the process of shape morphing in general, soft robotics, besides what you're doing, what are other interesting possibilities to get the shape changing? And there's other techniques, do you think maybe worth maybe discussing, or maybe they're still not very understood very well? Yeah.
Yeah, so I mean, I guess I'm generally fascinated by shape morphing. I mean, if you look at biology, it's so advanced with what animals do, and even plants, frankly, in nature, with how they can adjust their shape, adjust their geometry to do different things. And I mean, certainly in soft robotics, many people love the octopus due to this really amazing ability to reconfigure its shape, to squeeze itself through these tiny holes. Is really quite inspiring, I think, for this field. And so, when we started looking into shape morphing and how people are doing this, we kind of focused on a few different things. So again, we wanted complex shapes. So there's been again beautiful work with origami and kirigami doing that. Also, locking shape again was something that we are interested in. And when you're talking about locking shape, you can do that with these phase change materials. You could do it with kind of magnetic sort of properties. There's also electrostatic approaches people have been looking at, and there's a variety of ways to lock in place. And I think one of the things that is a differentiator within that set is how much power does it take to hold that shape in place, or how much power does it take to go between different shapes, and both of those are considerations when you're thinking about what you're trying to achieve. And then the other aspect we were really interested in was the reversibility aspect, and we've seen, I think, some really great work with pneumatic actuation, where you either pattern the essentially the channels that the pressure is flowing through, or you pattern the materials so that they have different rigidities in different locations. And when you utilize those approaches, you get different amounts of change across a sheet. And those different amounts of change then allow you to have different ultimate structures that are developing as you're applying these pneumatic pressures. And again, those are really fascinating. I think also from the materials perspective, in terms of achieving those kinds of morphable shapes, we've seen really great work with liquid crystal elastomers, where you can actually program the molecules so that when they go through their transitions, they end up achieving different configurations. So that's a really neat sort of molecular control over shape morphing. And then I think in general for actuation, if you can essentially distribute how uh, how the deformation is occurring across a sheet, that will ultimately allow you to change the shape and the configurations that you can get into. So, we've seen again work with small scale actuators, with fibrous sort of actuators. Carbon nanotubes have been used for those kinds of things, and I think ultimately, as a field, if we can begin to, um, you know, figure out really synergistic ways to combine these different material aspects with the different structural aspects, and then achieve actuation within that. I think sort of the holy grail of so much of this work is being able to effectively have a material and pixel by pixel control, what the shape might be or what the rigidity might be. And to get back to the octopus, it's interesting because they have effectively, or I guess generally cephalopods, they have the ability to change the local topography on their skin to induce camouflage, which is really fascinating because they have this kind of local control, but then also they have the ability to change the global shape of that system. So as we kind of push towards morphing materials, I think this pixel by pixel control of stiffness, of shape, of any kind of functionality is really what a lot of people are pushing towards. But of course, it's also one of the most challenging things that you can imagine. And I think that's where a lot of exciting work is happening. Again, people have looked at magnetic approaches for this as well, where they can kind of program and orient the magnetic domains. So there's a lot of rich approaches, and I think right now it's kind of every day it seems like we see a new and exciting approach to achieve these kinds of functions. So it's a great place to be right now in this field.
Yeah, great. Maybe I want to ask you if there's something you disagree with when it comes to shape morphing. Maybe in soft robotics field, you see certain approaches. Yeah, I don't think this may be maybe the right approach, or maybe you don't agree with the approach. Is there something you disagree with?
I would say that if I were to disagree with something strongly, it would be because I have the solution to it. And I don't know if I have the ultimate solution to it right now. I mean, I think generally we do have to think about what we're trying to achieve, which aspects are important, because I think we've seen people do things now trying to do soft robotics for like drug delivery within the body, and the demands that you would need for that are probably very different than what we would need for a robot outside of the body, or a big robot outside of the body. Um, so I think different applications probably have different approaches that are going to be most useful, most powerful. Um, so I would kind of at least from my perspective, seeing how things are developing, it's hard to say that one approach is wrong or one approach is right, but I do think that certain approaches have strengths and weaknesses in different applications, right? I mean, for the magnetic actuation, for example, you know, I've seen people starting to talk about putting these like kind of like magnetic robots in the body, and getting them to move through blood vessels and channels and all this, and it's been amazing to see that work. And there's aspects of that work really well within the body that probably wouldn't work very well if you wanted to throw a robot out the window and have it go do something else. It's hard to apply the magnets potentially in a vast open space. And in the same way that we utilized some phase change characteristics. So again, we did this kind of reversible plasticity mechanism, which allows us to do everything at essentially room temperature. But when we do want to go back, we have to heat it up, and 60 degrees Celsius is something that you can kind of hold in your hand for a brief amount of time. But I would also, I don't know if I would want to throw that into somebody's body and say, you're going to have this on for the next hour. Deal with it. So again, I don't know if there's a right or a wrong, but I do think that certain schemes work better in different environments.
Maybe I want to go back again for the multi-material, because that's also, I think, the scope of the paper, multi-material. When we speak about the pattern and multi-material, if we combine different material, maybe mechanically, properties differently, how do you see the pattern can be investigated? For example, in the paper you have certain pattern, but when you try to design, I will design this multi-material, and one material has certain pattern and the other one. So how do you see this combination of the multi-material? Do you think you understand how combining different material can give us very interesting features? Do you think that's something we understand, or maybe from your experience?
Yeah, so I mean, I think ultimately, multi-materials are going to be really essential for soft robotics, and morphing materials and a lot of these, let's say, soft matter technologies. Um, we love elastomers. I use elastomers all the time. They're great. They're soft, they're stretchable, they feel like tissue. Um, but they lack a lot of the functions that we need for robotics, for morphing materials, right? So I think the integration, the incorporation of multiple materials is, I don't know if it's essential, but it seems like it's really enabling for a lot of the directions that we see moving forward. And, in our paper, again, trying to tackle this challenge of being soft and deformable, yet rigid enough to support loads, um, that is a problem that can be tackled with multi-material integration. And I think along those same lines, one of the, I think, the real feats of this paper that probably are not at the forefront of what everyone sees is that we were able to make this thin metal endoskeleton with these highly architectured features. And what was challenging about that was, so we eventually came up with a process, and my graduate student Dogi Huang, who was the co-first author on this paper, he developed this approach to do this. And so we then had this metal endoskeleton, which was great. It was this very beautiful architectured piece of material. And then we had to take that and we had to incorporate it into an elastomer, and we had to incorporate a heater into that. And then we had to take that entire sheet of material, and because we're using kirigami, we have to cut that up. We actually had to, in our case, laser cut these features actually in between rather thin lines of our metal endoskeleton, because the metal endoskeleton was patterned in a similar way as to the kirigami. However, the metal endoskeleton was also continuous, while the kirigami cuts were essentially discrete or localized. So, when you bring multiple materials together, it also opens up, I think, challenges and opportunities in fabrication of these devices and devices, materials, and robots. So yeah, I'm a big fan of multi-material integration to solve these problems. And certainly in this paper, and in the work that we're doing in the lab, there's a lot of emphasis on taking a material that can give you this function, a material that can give you this function, and trying to understand how you can bring those together to get synergy without losing those really nice capabilities that you brought them for. So I think that is a big opportunity both in material design, material synthesis, fabrication, integration. I think it's really a promising avenue for a lot of the challenges in the field.
Mm-hmm. Maybe I'll ask you, if you change the pattern, if we assume that you change the pattern, would you change the trade-off between being soft and stiff to hold the object and still stretch? Do you think how the likelihood would change the objective here?
Yeah, absolutely. So we do discuss this in the paper. So in our approach, the geometry is really essential to the function, and the material that we use is also essential to the function. So, we show in the paper that, and I think you can kind of imagine this, if you have a sheet of material, in this case, let's say a piece of rubber, and we put this kind of metal endoskeleton within it, when we deform that rubber, if the metal endoskeleton is too rigid, it's too hard to deform it. if the metal endoskeleton is too soft, what happens is that when you deform it, the elastomer, that rubber, actually has enough restoring force to pull it back to where it originally started. So in our case, the way that we treated this was effectively with the kirigami, you create an array of beams. And we know the stiffness of a beam depends upon the material it's made out of, as well as the structure. So things like the thickness, how wide it is, how deep it is into the plane. And we had to carefully tune the stiffness of the metal endoskeleton to the elastomer so that when we, take the material and deform it, it can be deformed. But at the same time, when we reach the point that we want it to fix into shape, when we let go, we want that material to stay there. So the metal endoskeleton has to be stiff enough. And I would say that, one of the advantages we found here in terms of bringing geometry and materials together was that both the metal as well as the structure, they go through a nonlinearity, which is to say that, when you take a kirigami film, what happens is that when you first pull on it, it's kind of stiff. And then at some point, it becomes much, much softer. And that's because these cuts effectively open up. And when they open up, you then get the ability to deform them much, much, much more without increasing a lot of the mechanical energy in that structure. And at the same time, the metals that we use also, they go from an elastic response to this plastic response. So I think, one of the things that we found was the ability for the material to plastically deform, the ability for the structure to go from stiff to highly extensible. If you kind of match those up, you do get the ability to significantly deform the material without putting a lot more energy into the rubber to pull the entire thing back to where it started. So there's a big element of design when we put, trying to get the sort of maximum performance in this system.
Maybe a good question here. What should be considered when you're matching the transition from being soft to stiff and matching to stiff? Is there something you should consider in this? Yeah, very, very important.
Yeah, I think it's really important. And so and the thing too about kirigami and origami in general is that when you begin patterning these materials with cuts or folds, you open up a huge parameter space in terms of what you can vary. Whether that's, as simple as like how long a cut is, or maybe as complex as, what is the structure of the cut as you go across the film? Does it change? Is it the same? And by doing that, you can begin to induce, different properties across the sheet. And that's been one of the, I think, real hallmarks of origami and kirigami is that very quickly, very rapidly, you can take the same material, control the structure, and you can induce a huge range of properties across that sheet. And for what we're trying to do with utilizing these structures to hold the shape, it became very evident to us that we kind of had to focus this initial study on a relatively let's say small parameter space, because otherwise it opens up a huge design space that would have been really hard to tackle. So from how we look at this kind of going forward, I think there's a lot of opportunities to potentially spatially grade, so change the cuts, for example, as a function of position, to change the thickness or different properties of these endoskeletons as a function of position, so that then you can induce properties in different directions, properties at different locations. And I think that, is a really exciting possibility, getting back to that idea of, pixel by pixel control of properties. Maybe origami or kirigami has a place in that kind of design space.
Mm-hmm. Maybe I want to ask you again about the cut. How do you make sure the failure, or maybe if we speak about the fatigue, the crack, if we make a cut, how make sure this a sweet spot here, that make the function here, but not really fail after a certain time?
Yeah. So that was something we thought about a lot because certainly when you add the cuts into the material, the stress is going to concentrate, at the tip of that cut, and there's been a lot of people who have studied ways to mitigate the stress near the tip of the cut because that can lead to failure, to fatigue, those sorts of things that we want to try to avoid. So for us, we found that at least in our materials, we could pattern them in geometries that worked for shape locking or shape fixing, and we could deform those about twice their original length or 100% strain, and they would maintain their integrity. So the endoskeleton wouldn't break, the elastomer wouldn't break, there wouldn't be things like that. Um, and we could actually, go there, and then we could heat it up and come back. We could go there, heat it up and come back. And we could do that. I think we showed maybe 10 cycles in the paper. Um, One of the other things that we looked at was what happens when it does break. So we did some experiments where we took the material, we deformed it, and then we broke it by hand. So we effectively like kind of cracked that endoskeleton. And it turned out that one of the benefits of utilizing this metal, which goes from a solid to a liquid, is that when we heat the metal back up and melt it, the two liquid fronts can actually come back and recombine and effectively heal that crack in the skeleton. So, I think there's an advantage, again, having that heating component, having these materials that do go from a solid to a liquid. There is some opportunity there to I think mitigate failure through healing, and be able to do that. I think we showed it over a number of cycles. I think it was maybe again 10 cycles where we broke it, rehealed it, broke it, and rehealed it. So I think that was one of the ways that we kind of approached this as well, was to I guess we kind of got it kind of by luck in a way, but the self-healing capability was good for making it more robust.
Yeah, I really like it, the structure and everything. Yeah, maybe of course, so close to the end, I have a question for you. But the first one, maybe we're still missing when it comes to shape morphing. If you can't just, when you have this look about the shape morphing in the field, there's something missing. What is this thing maybe missing still?
Yeah, I mean, I think again when we looked at this, we wanted complex shapes, hold the shape, go back to original shape, and one of the things that we looked at here was the speed at which we can do that. So with what we did with this plasticity mechanism, it turns out that we showed in the paper where we kind of threw an impactor at a film. We found that when the impactor hit the material, it induced a very significant deformation. And when we removed the impactor, that structure was held in place. So effectively, we were able to very rapidly transform from a simple sheet to a very complex shape in about 0.1 seconds with this plasticity mechanism. However, although that was very fast, when we do turn on the heaters and we want to then melt the metal and then allow that elastomer to bring it back, that can take tens of seconds, minutes even, for the material to melt, to come back, and then to resolidify. So we were able to make it very fast in one way, but there is still more to do in terms of making it fast all the time. And again, this is where I think what's so fun about this space is that right now there isn't one approach that is so much better than everything else, because they all have their advantages or disadvantages. For shape morphing, we've seen again really fast actuation sometimes at small scales, as I mentioned. We've also seen things like electrostatic, so like dielectric elastomer actuators, DEAs. Those are great at moving quickly, and we've seen these Hazel actuators as well, these kind of fluid-induced deformations, and those can be very fast. So that's really exciting from that perspective. But in some of those, I can't be too critical of the success we've seen in that area, but they do take a fair amount of voltage, which everyone is really working to push down. And sometimes you have to, keep the power on, for example, to maintain a shape. So they're super fast. They can be very efficient. They overcome some of the disadvantages to phase change materials, let's say, but there are advantages to phase change where they do have things that work better than something like a dielectric elastomer actuator. So in terms of what's missing, to get back to the original point, I mean, if we could, I guess, create one approach that is fast, power efficient, holds shapes, can go to different shapes, can allow it to be, I think, perform multiple functions. So, one material can do a lot of different things. I think, and there's probably even more to that, right? It has to be able to also take, other components on board that it needs for whatever function. But I think that's what we really want to get towards is fast, efficient, can hold shape, can go different shapes, and can do this all while carrying everything else it needs, and we're not there yet by any stretch. And it's certainly something that a lot of people are looking at, kind of even as you mentioned, Marwa, early on was, how do you power it without giving it power, right? How do we maybe harvest energy, or how do we get energy from the environment that we can utilize for what we need? I think those are some of the big challenges that we still have.
Excellent. Maybe two questions left for you. I think the first one, if there's any crazy ideas when you think about it for shape morphing, sometimes beyond what we have in, realistic, but sometimes I imagine shape morphing would look like.
I guess I can kind of bring it back a little bit to what we talked about in terms of, pixel by pixel control. And again, I think biology does this beautifully. Again, the octopus can change local shapes on its skin, can dramatically change its body shape. So it has like all these levels of reconfigurability. And I still think and I've been thinking about this and trying to push towards it in some ways, which is how do we get systems that are more lifelike, that we can control, pixel by pixel, incorporate sensing, actuation, energy harvesting. How do we make it so that, again, if we look at biology or nature for inspiration, I mean, the octopus, like a lot of things, they process everything on board. They carry all their own power. They have these amazing functions. If you chop off one of their arms, it just grows a new one. So, for me, shape morphing, I guess it's going to come back to, fully integrated sensing, actuation, computing power, and also probably healing. The ability to regenerate, to be regenerative, is also really exciting. So, I mean, I think that's kind of the craziest I can think about would be to get, all those in one material, and really push towards, things that are more lifelike, that don't require, big hardware, things of that nature. So, I don't know. Maybe we'll get there in the span of my career or everyone who's working on these things. But, it's certainly a very exciting possibility, I think.
Wonderful. Maybe the last thing, there is something was counterintuitive sometimes. I don't know if you encounter, maybe in this paper or maybe in your work, something was counterintuitive. It doesn't make sense, not explicable yet.
Yeah, so something that's counterintuitive. I mean, I guess the most counterintuitive aspect of this for me is how do you make something which is soft to deform yet stiff to support loads, to be able to incorporate different functions. This was also something I looked at in the past in terms of controlling adhesion, was to make a material both soft and stiff simultaneously. I mean, they're completely at odds with each other, right? And it turns out that for a lot of, at least in my lab, a lot of things that we want to do, we often are stuck in this position, right? where it has to be soft, but it has to be stiff. And for us, that's an exciting place because then you can begin to think about incorporating, new materials, new geometries, maybe have those properties or geometries change over time, whether that's, through a programmed response or maybe some kind of stimuli turns that on. Um, but for us, I think that's an exciting conundrum to be in, to be soft and stiff. And that opens up just a lot of, I think, opportunities to engineer materials, to design the structures. And then ultimately, for us, I think in this community for soft robotics, how can we leverage the softness and the stiffness while also incorporating, the different components that we need for the robotic function itself. And again, this was something that we looked at in this paper was to try to make these materials so that they were deformable, yet be able to hold components and sustain the propulsion that we needed for these different modes. So I guess, to get back, we had this multifunctional drone. It drove and then it had to change shape and then fly. So that combination of soft and stiff was essential, and also integrating the components. We also had this underwater vehicle. So this is a lot of work done by the other co-first author, Ted Barron, where we had this robot that effectively was a flat sheet, and then we deployed it into this, let's say, a state that could be functional underwater. And again, we had to do the same things. It had to be soft enough to deform, rigid enough to maintain shape, but also have the ability to incorporate, in this case, pneumatic actuation. We also used, water-based propulsion, and we had to put the heaters, inside these materials as well. So again, I think that's something that we're thinking a lot about, soft and rigid while also being functional. I think is really an exciting place to be. So.
Yeah, again, I really like this paper so much, and I don't know if you have any final words you'd like to say for people listening. Any final words you'd like to say?
Yeah, I mean, I guess I just want to say that, this was a paper that took, for a lot of people, you get to see the final product, and it's I think some work that we're really proud of. But the reason that this was successful was really because of my students Do and Ted, and I also had a postdoc, Hawk. I mean, they worked tirelessly to get everything to work, to understand how it works. So, I would really want to say that, this is a very exciting paper, and it is a paper that also, really forced us to think hard about what we were doing, to work hard to get things to work, and then also to try to put it together so that we could explain it to the reader and make it something that could be compelling and hopefully inspirational for some people. So, this was definitely one of those papers that we really enjoyed working on. We had great feedback from people in the community and the reviewers that really helped push the paper forward. So I definitely am just very appreciative of all the feedback and support that we got. I just really want to give a lot of credit to the students who really made this possible. So it was a very fun project.